Nope. What was the question? Let's answer it for everybody.
Alright, so there's a concrete column here.
Correct.
You're going to show that the PFC is connected to a concrete column.
Just squeezed in there. Can you see the little red line just in there? It's not very easy to see.
Yeah,
Let me go through it.
Okay.
Yeah, good question. Quite right. Good question. All right. So you'll have noticed in the chain of strength diagram that some of the elements are black and some of the elements are red. The red are highlighted because that is the actual chain within the construction system. That is the chain of strength. The principle of the chain of strength, which is unique to the Northern Territory or to cyclonic areas and the way we interpret our construction in regards to cyclonic conditions, the principle behind the chain of strength is that every single component of the building is connected into the ground, because cyclones tend to want to lift structures away, lift up and away. So the idea is that if everything is if everything is connected to structure that's tied into the ground, the likelihood that that can be lifted up and carried away is much less. The principle of all our cyclone cleanup to pick up debris and take it away is so that there aren't flying objects. So not only do you want to keep your roof on your house to keep the rain and the weather out so all your belongings aren't ruined and you're safe in your own home, but it's also not to create further debris that might impact on other buildings and create destruction in that way. So the first part, and I probably should update this now just a little bit more, the first part is to connect the roof sheeting to the battens that are on the roof. So our cyclone washers have a little cap, there's the grommet underneath to prevent water from getting in, and they're connected every other crest into the battens at 900 centres. So these are roof battens. These are drawn like timber. The little section shows a timber section. These are battens, and they run perpendicular to the truss, and the roof sheeting is connected to that. The most common footage you'll see in construction failure in a big storm might be that the roof sheeting will peel off and the battens will still be connected to the underside of the roof sheeting. Has anybody ever noticed that in the news? Next time we have a storm, you might see it in the footage, and you can probably do a Google search and find lots of footage of roofs that have been damaged, and you often see the roof sheeting peeled back and the battens are still on the underside. So that connection with a screw fixing through the roof sheeting into the batten is often quite strong. But of course the next level down, the next link in the chain, if you like, is the connection of those battens to the roof truss, because obviously the roof sheeting has to be connected to something. So the next level down is the batten to the roof truss. Now you can fix that in multiple different ways depending on what the batten itself is. If the screw for the cyclone washer is long enough, you can go through the batten and into the truss as long as it's sufficient, deemed to comply. Or you could use an over bracket or a strap that connects the batten to the truss, a bit of steel that goes over the top and fixes both to the truss, so it twists. It goes up and then over and down on the other side, so you can see it. And the Deemed to Comply manual has a copy of that you can have a bit of a look at. So it's a bit more old-fashioned, but it's an over bracket. Then everything that's connected to the trusses has to stay on the walls. So we're not talking structural loads and things like that, but that's a part of it. But the whole down is about connecting everything from the top down. So the trusses get held to the walls, and there's an over bracket for that too. It's heavier steel than the light gauge over bracket for the batten. It's quite heavy gauge steel, and you can see it in section here. This is a little mini detail taken off of this area here. So this is the plate, the bottom plate, this truss bottom cord of the truss here, and the vertical is the top cord that you can see in section here. And you can see the over bracket goes across, up and over and down, and it's a single piece of steel, usually fairly thick, about 8 mil thick if you're lucky, and it has pre-punched holes through and down so that bolts or screws can go through, typically bolts, can go into the concrete or into the framing or over the framing and through and then bolted underneath, and then up and over and bolted through as well. So 3 points. The 3 points is for very large trusses, sometimes for a smaller truss that isn't going to be affected by as much uplift, you can just have a cleat, an L cleat on the side. You don't have to have a full over bracket. That's for a big girder truss. You can see here, this is looking at it this direction, so in elevation view if you like, and the small thickness at the bottom here has a pop-up as well. The hold-down bolt that goes all the way through the walls pops up through the bottom and is this little section here that bolts through. These are long threaded rods. They're not necessarily threaded the entirety of the rod, but at the top and the bottom it's threaded so that you can put a nut on the top of that, put it all the way down the wall framing and through and down into the PFC bearer. So there'll be a hole punched in that PFC bearer and then you can put a washer and a nut on that same threaded rod. So typically in timber framing, it's different for steel framing, but typically in timber framing you'll see the stud and then the hold down bolt directly adjacent to it. Now there's locations to include those. You have to have hold down, and you can write this on there, you have to have hold down bolts in every corner, adjacent to every opening, and then at 900 centres between all of those. So that's the rule for hold down rods, and it's definitely something you'll need to include in your report. We're going to have to verify that the framing that we receive has hold down bolts, and if it doesn't, add them, and if it's got them, what condition they're in. Because if they've rusted and they're not going to perform under cyclonic conditions, they'll have to be replaced. Every corner, adjacent to every opening, and at 900 centres everywhere else. So let me just explain what 900 centres means. I'm just looking at our floor plan here. I'm just going to draw big red lines. This is not typically the way that you would illustrate hold down. You would use little dots to represent the red. The red dot would represent the actual rod itself, but you're not going to be able to see that from the back of the class. So I'm just putting big lines for now. Everywhere the wall changes direction. I'm just thinking. I'm going to put it here because I'm not sure if it's actual wall framing or whether it's just cladding, but it looks like wall on the floor plan, so we'll put it just to be sure. To be sure, to be sure. No, they don't. How are we looking? Have I got all the joins? Oh, here it is. Yep, thanks. There's no wall there, it's just joinery.
No, the door.
I haven't done openings yet, I'm just doing walls.
Yeah.
So I missed anything? So I think I've got everything. So all the intersections, everywhere there's a change of direction, wherever a wall meets, all the different instances where you'd like hold down. Then we've got adjacent to every opening. And here you've got them quite close together, but you'll probably still do it.
I have in the windows.
Adjacent to every opening, doors and windows. That's the same one there, so that's a single. Full height, 2.7 metres. No, this is upstairs walls. I missed any openings? Yep.
If the windows were internal, would you have to put one there as well?
Yep. Anywhere that there's a space where there are no hold downs, you then divide that width by 0.9 and then round it. You can't obviously do it exactly, but let's have a look. What have we got here? Is that 4.5 metres? The width there?
Yes.
Yep. So we'll leave the wall width off because that's taken care of with the corner hold downs. So if that's 4.5 metres, is that, 5 metres?
No, 4.5, you get 5.
Yeah, it happens to divide out real nice. So I need 5 of them. Nope.
Yeah, include the corners of this.
5 are the included
Is that right?
at 900 mils.
Yeah.
5 spaces.
You just put one centre and then 2 on either side.
Pardon?
Put one in the centre and 2 on either side.
Yeah, that's what I was thinking. Is it 2 or 3? 1, 2, 3, 4, 5. It's not exactly the centre. It's more like there, 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 and there. So 9, 2, 3, 4, 5, 9's are 45. Beautiful. That was harder than it needed to be, but you get the idea.
So when you put a draft in AutoCAD and Revit, you can just say
Divide.
online and divide it into 5 equal space.
Yeah.
It's not doesn't come out to be an exact 900 between. It will give you equal distance of 5 bays.
Yep.
In the breakup.
So then you go in and add to a maximum of 900 centres. So if I've got a stud, a bottom plate, and another stud, they're typically at 450 millimetres apart. So the centre line and the centre line of those 2 studs is 450 millimetres apart. So it's not from the inside of this timber to the inside of this timber that's 450 millimetres apart, because I don't necessarily know how wide this timber is going to be. So I dimension to the centre line, and then I simply just specify the member size on the drawings. So the centre line, which is a fancy little symbol with a C and an L that overlaps it, the centre line dimension between timber studs in wall framing is 450 millimetres for cyclonic conditions. That's not the case everywhere, and that's the maximum. So if you can't fit it in, then it gets less. It can't be more, but it can be less. So a maximum of 450 centres. The hold down is a maximum of 900 centres. So on this particular wall, every second stud would have a hold down bolt right next to it. So the 900 centres. No, what?
So does that mean, is there a maximum size?
No, so you do, we'll get to that. If you have to put a door in, then you have a jamb, and then you have the studs divided out between the doors and windows to a maximum of 450 centres. Hold down. Every corner, adjacent to every opening, and then 900 centres everywhere else, whatever's left.
So 900
A maximum of 900 centres.
centres is 0.9 of a metre?
Yes, 900 millimetres. 900, yep. If I don't say, I mean millimetres, because that's the universal unit. Everything else I'll specify.
Is there a symbol for hold down bolt?
No. HD bolt. So that's a peculiar phenomenon. Now we were talking about our hold down bolt in regards to our chain of strength diagram. Looks like a cool diagram without the floor plan, doesn't it? So it comes down and it needs to go through something and be connected underneath so that it can't be pulled up. Now obviously, if maintenance has failed or water has been allowed to pool here, rust can form and the strength of that hold down can be diminished. So when we remove the internal cladding or perhaps even the external cladding for inspection purposes, we need to inspect the hold down for structural integrity. We need to make sure that old steel is still in as good a condition as it should be to perform the way it was expected to. And if there are any hold down bolts rods that have been deteriorated, they'd need to be replaced. So that will definitely need to go into your report.
Guitar strings? Like are
They can be quite taut, yes, yes. Not so that you would have failure in the material, but to fairly significant tightness, yes. Oh yeah, I don't know how that might go, to be honest. Has anybody ever installed a hold down? Have you ever installed it? Yeah, that's a bit different. So through the PFC, did the PFC do the rounds? Has everybody seen the bearer material? I think it's just near Despina there. I'll just grab it. May I? Just the PFC. Thanks. Muffles. So this is a very small version of the bearer material. It's called PFC, Parallel Flange Channel. So these are the flanges, and they are parallel to one another. So that's called a parallel flange channel, C for channel. So we're not creative here, just keep it obvious. So here's our PFC. There would need to be a hole drilled in the top here for the rod to pass through. There would be a washer underneath and a bolt fixed to that threaded rod. And that would sit in there. Then the PFC would sit on top of the concrete column. Inside the concrete column we've got reinforcing. Now if your builder is particularly clever, the reinforcing will be a single piece, but that's pretty unlikely because you'd normally pour the foundation, the footing first and then the column on top. So I've not drawn this particularly well because there needs to be a section here where it changes from being inside the footing to being above ground. So this is sort of where ground is at this point. And actually I should probably put it a bit lower because it's actually at the bottom of these hips. See how there's a decline on the top of the footing concrete? That's to shed water. So you need for rainwater to stay away from any connection here, whether it be steel or concrete. Water is the enemy of good building materials, so we really want to keep that water floating away as best we can. Has anybody not had a chance to play? Did you want to pass that around? Thanks. Inside the concrete of the footing, there's some steel reinforcing in there, and it'll be splayed at the bottom with a cog that will prevent it from being able to be yanked out under force. And when you think about trying to get steel out of wet concrete, it's actually pretty hard, but dry concrete that's cured and things like that, you would imagine it would be extremely difficult. But just to be sure, we have a little splay at the bottom to make sure that it can't be pulled out. I probably could have done that at a proper 90-degree angle. And then the reinforcing either sticks up on its own and then it's connected further, or it just is overlapped inside the concrete like I've drawn it. So it's not the best drawing you've ever seen, but it gives you an idea. And then the concrete is poured on top and the reinforcing is overlapped so that there's a continuous overlapping of reinforcing within that concrete, and then the new reinforcing sticks up out the top, and you can just see it's folded over and welded to the underside of that PFC bearer. It's not the best detail you've ever seen, but it just gives you an idea of the connection. The other option is to poke it up through the bottom of the PFC and wash it and nut the top off it as well, so you can have some threaded rod there as well. lots of different ways that you can do it, but as long as it's connected and fully welded. So we have like a minimum size weld that you have to use. It has to be nice and continuous, 6mm fillet weld, and it's fully up and down the side of the reinforcing.
So what is the whole down the road?
Yeah, steel. No, not typically galvanised because they're protected inside from what you would need galvanising for. So what do you use galvanising for? Do you know? Weather protection. So if the hold downs are inside the wall, they don't need to be protected from the weather so much. So you wouldn't pay the extra expense to galvanise the rods. If they're exposed, that's different, and we'll talk about that in a bit. But they're just steel rod. Yeah, that's right. Galvanising won't help. This is galvanised, the silver here, but the PFC isn't. Yeah. Yeah, cool, all the fun stuff. Rust is bad. Yeah. In the end, beg your pardon? Or are we just talking about rust? Yeah. So in the end, everything is connected to the ground. It's a continuous chain all the way from the top to the bottom. And the idea is that should a cyclone inflict its fury on the building, that it will stay where it's supposed to.
When wouldn't it be though? What place in the world just builds a box and sticks and doesn't tie them together?
Everywhere that doesn't get cyclones. They just sit.
Yes, so the downward force of the weight of the roof will, they're connected, but not.
They're fixed in place, but not as strong as that.
We rely a lot elsewhere on just the weight of the construction itself and the downward force of that, bearing onto the wall plate and bearing onto the floor bearers, and then coming on down to the foundation. Yeah, I never had dealt with this uplift until I moved to Darwin. Yeah, it was always about the downward pressures, but here it's all about the uplift.
Good job. Chain of strength. So it'll be needed to be maintained. It'll need to be visually checked to make sure it's still in place in the transportable building we're getting. And then it'll need to be repaired and enhanced if it's failed to bring up to compliance. Now there's another phenomenon that we are likely to see in this particular project. I want to be able to open that in another. Okay. In the downstairs area, we're going to have quite tall, slender columns. Yeah. It's another wind issue. So if you imagine we have our lovely building and it's propped up on columns. End of story? But if the wind comes along and blows on it on the side and it hits the elevation, this narrow elevation is less of an issue, but imagine if it hit this one and started to push the other way, it might be a bit of an issue. What we end up with is a phenomenon called raking, where you end up with a building that topples over sideways this way. It just goes, and we don't really want that. So the concept of cross-bracing, and there's no guarantee that the storm will come in that direction, so we can't just do cross-bracing in one direction, we have to do it in all four directions. The idea is if we put bracing and we triangulate, I'll do it for all four just to be sure. It's not going anywhere now. So if the wind comes in this direction, this brace here wait. So bear with me. Is that right? So if I push on here, it'll be, the force will be going this way. It'll be pulling on it, and this bracing will resist that. Took me a minute there, sorry about that. My spatial awareness is letting me down this morning. If the winds go this way, then this side will hold on to it and prevent it from going anywhere. And vice versa for if we were to turn this into a square, bracing that might go back that way, back the other side, if we were to do the same, and along the back as well.
And then the owner comes along and wants to put his car in the centre.
Yeah, yeah. So that then leads me to how many are we likely to have? Now, there'll be a unit of competency that you'll do, and this is what it looks like. And this is a typical way that you might connect it. You might have a D-clip top and bottom to the columns themselves, and then have a tensionable connection in the middle, or they might simply be directly across. And then they're threaded at the ends here, and you can tension them a little bit, because you don't want them to get loose. I think there's another diagram that might be an image. Oh, that's the detail itself. So that's the connection at the bottom with the little D-clip. And then the centre.
Is that rod or braided chain?
It's rod, threaded rod. So it's not threaded the whole way, just at the ends. Yep, so it has a screw thread at the top and the bottom. And what have we got here? A little document about bracing. Oh, it's the same images. I knew that. I could have opened that itself, not to worry. So what we want to do is have a bit of a look at our site plan. Now remember, this is what we had originally. This is what the building would have looked like with concrete columns when it was still built on the base before it got cut off at the knees and taken away. And you can see these little squares to represent where those concrete columns that would have been about 200 millimetres by 200 millimetres, those are the concrete columns, and then we've got the load-bearing laundry wall as well as doing some work. This is what we had originally. And you'll notice it's a fairly consistent grid layout. We've got some special steel columns here for the stairs. They're unique and in places that are required for the stairs themselves and are sort of an addition. And we've got a little column here underneath the landing for the stairs as well. So they're a bit different. I colour those in black so we keep those separate. But we have this grid layout. Now, these centre lines that are sitting across represent the bearers that are doing the work, that are made out of that PFC material that we just talked about. Now, it's at that bearer level that we will get the house back. The bearers will come to us. That's what the floor joists are sitting on. So you can't really have a house without joists or bearers. So they're the material that we'll get back from the PFC up. But we're going to have to put some columns in place to support those bearers when it arrives. And they'll sit across the columns. So we'll have new columns, most likely made out of steel, because the concrete is quite expensive. And takes up a lot of space and is a bit unnecessary and a bit outdated. So I'm predicting everybody will agree with me that steel columns would be preferred over concrete columns. Cheaper, quicker, takes up less space, looks nicer. All those construction issues. So if we're saying we're specifying SHS, square hollow section columns, which I have a copy of over here, probably 100 by 100 millimetres wide, that's this one, and about that thickness. It's probably 4 mil thick. So an engineer would determine the size of the columns. But if we want this shape, we don't want rectangular, we don't want circle, let's say we want square, then we can say that architecturally. I expect you've seen a bit of that, yep. Square hollow section, SHS, square hollow section. In section, it's hollow and it's square. When you look at it, like a telescope, it's square and it's hollow. That's how you remember that is. Not
The other options are rectangular hollow section.
Yes.
Rectangular hollow section.
Yeah, yeah. R and C. Yeah, rectangular and circular. Let's say we're specifying that to our 3 metre height. So we want the height to be 3 metres. They might sit where these same columns sat, and then the bearers would sit directly over the top. Now the reason why it's a good idea to replicate the original grid is because then we know that the load span will work. So we know that the bearers can reach from here to here and from here to here without sagging in the middle. We don't want deflection from our bearers because then that makes our floor wobbly and it's hard to sit still when you're eating your dinner. So let's say we were going to put SHS columns where these columns used to be. We can still drive in between those, no problems. The carport would still work. We might have our blockwork wall here instead of columns. How about that? Remember the client said they wanted a wall at the back of the house, somewhere to put a kitchenette and some clothesline and an air conditioner on the outside. The services could then run down here. Wherever they needed to go, we could have the air conditioning condensers on this side and the clothesline here. How's that? And then we'd have our laundry where it belonged before as well. How about that? You'd move the laundry? Why? Just to make it difficult? Well, we were planning on it being a cyclone shelter, the laundry. Yep. So there'll be pipes running down from the bathroom underneath, and we can bring pipes together and then down the drain from underneath. One of the handy things about elevated houses is the pipe work is easy to access and move around, so that's not too bad. We'll leave the laundry with this for now. We won't make life harder than it needs to. But what we're now looking at is a series of columns, the ones that I just drew looking at the front of the building. We've got a series of columns now that all might be subject to that raking force should wind push on the side of the building. And considering the location near the coast, the likelihood that we're going to get a nasty storm is pretty high. So we definitely want that bracing, don't we? But we can't put bracing here because that's where the carport is. That's where we want to drive in, isn't it? Yeah. And we can't put it here because that might be where our access is for foot traffic to get to the stairs. The laundry will help. We could probably get away with a bit here, couldn't we? Yeah? Where else could we put some bracing? This is the pool area out here, so we don't really want any bracing here either, do we? People will walk into it. Yeah? What about here?
Yeah, other side.
Because that's the back boundary, isn't it? And we're not really encouraging traffic that way, cars or people. Perhaps here? This is where the stairs are coming down. There's not a great deal of accessibility under the stairs, if you like. It's not really an expected thoroughfare. So perhaps here we could get away with some. Now we'd have to start talking to the engineer. So there'll be an engineering solution about how many cross braces we'll require, how big the rods need to be, how they need to be fixed. They'll have their own prescribed notion. But we're at least proposing some of the ones that we can suggest might be okay for our design for potential locations for cross bracing. We could put some here. I don't love the idea, but we could probably at a push, take it. But we've got the whole full wall here would be acting as cross bracing. Pardon? This one? You reckon we could get away without that one? My instinct says we could get away with that one as well, with the corridor. Yeah. You reckon where? Here? Oh, down here, under there.
No. Keep going over.
Just there.
More relay across.
You reckon we can get away with some more?
I reckon
Oh, yes, lovely. In the other direction. I like that. So in this vertical. Yeah, good point. What do we think? It's a proposal. We're not the ones that make the decision, but we would perhaps want to guide the engineer away from thinking about where our traffic, our pedestrian traffic, our living traffic might be, and ask them just not to put cross bracing in those locations. So I would recommend adding some sketches to your existing drawing, some notes about cross bracing, and our proposal of where we'd like them to go, so that they don't get put right where we want to walk all the time. So we've got access to the pool, access to the laundry, access to the carport, access to the front yard, but we've still got some cross bracing to help us from falling down in a cyclone, which is kind of important. Otherwise, access to the pool is not so necessary after all.
And this is how you mark.
That's how I would mark it. So, and I would just annotate that. Cross bracing. Proposed cross bracing. B-R-A-C-I-N-G. Cross bracing. Just a little neater than I did, if you could. What do you think, Sandra? Do you think we'd get away with that?
Yep. Yeah, you probably won't need 4 on the back there. All the way down.
So yeah, I've got the question mark
Yeah,
on this one. It would be good if...
the engineer which ones you can drop.
Yeah.
I generally tend to mark cross bracing on the architecture plan, send it to the engineer and get some feedback there, because if you send it to the engineer first, they'll mark the cross bracing on where it suits them structurally, and they won't consider access. So they're not thinking about carports or where pedestrians need to walk. Structural engineers don't think about those things. They only think about the building falling down. So you're better off selecting your preferred locations and then having a discussion with the engineer.
So a couple of unusual construction phenomena that you won't see in the NCC. Australian Standards 1170 that takes care of all the loading, and the Wind Code 4055 will ask us to remedy the issues that cyclonic conditions pose, and we'll learn a bit more about that in the 4005 unit. But for now, I just want you to understand chain of strength and cross bracing and account for those in your report. Unfortunately, you won't find it in much of the textbooks. There used to be a fantastic Darwin Builders blog, but I think it's closed down now, and he was terrific.
Do you have one in between the cars?
No, so that you can walk between the cars easily. Yeah, you'd bump your head all the time climbing through.
About pan bracing.
Who the what?
Pan bracing. Pan bracing.
Pan bracing.
Yeah, where you would join all posts together, but
Oh, in the horizontal. Is that what it's called? There's an excellent example of that at the Coolalinga Shopping Centre, at the front entrance, as you're heading out. If you look up, the horizontal up there. If you want to see an excellent example of this in action, the Coolalinga Shopping Centre is excellent. It's just a big shed. It's a nice shed, but it's a big shed. Yep. And our Pink 9 office building, the Fancy Trade Training Centre, is a portal frame shed, which is just a grid, a very tall grid, and it's got massive cross bracing on the outside. It's excellent as well. Typically you would try and make it aesthetically pleasing or build it in so you couldn't see it. In this instance, we just try and make it look as pretty as we can. It's probably not necessary because of the bearers and joists doing most of that work. Yeah. So Kizzy was just saying, what about in the horizontal axis rather than in the vertical axis that we've been talking about? So if you can imagine, if you've got a building, a rectangle looking in plan view, if you were to start pushing on it on the side with wind and it started to just weaken on one corner, you would end up with sort of a trapezoid, I suppose. It would end up in this direction. Oops. It might end up sort of going in a twisting direction. It might create some torsion. And if you were to brace that this way or just in little sections, it would prevent that from happening. So you can do it in the horizontal plane. It's not necessarily something you'd see at this scale, but at a bigger scale like the Coolalinga Shopping Centre that I talked about, where the spans are very wide and the structure is quite sparse. It's strong in span, but it's a long way apart, so that torsion can happen quite easily. So they use the... Yep. If you want to remove structural walls and the ceiling might be affected in that way, you often have to put cross bracing in the ceiling to be able to keep the shape that you want, because the roof wants to do this. Basically, it's pushing down and out. If you take some walls out underneath, sometimes you can get away with it if it's structural, just by securing the roof in the horizontal plane. But that's an engineered solution. Don't be thinking that, just let the engineers advise about all that stuff. Any questions about chain of strength and cross bracing? Now we talked a bit about having to inspect the existing hold down rods when we expose the wall framing for inspection before we get it certified and make it habitable. Does anybody want to ask any questions about that? So what we're surmising, what we're guessing is that, sorry, is it too soon? What we're guessing is that the internal cladding that we will buy may well be either asbestos or just in really bad shape. It might be damaged in transit, or it might just need some fixing. The likelihood is that we'll probably remove it. It could be mouldy, it could just be too thin, it may not take paint the way we'd like it to. We just want a nice finish on the inside of the building. I would recommend that the internal cladding be removed, particularly if the external cladding is in still pretty good shape. If we visually observe that and we can see that it's in pretty good condition and we don't want to muck about with it, because removing cladding on the outside, if you muck with the metal too much, it can become deteriorated so that you can't reuse it. It might get bent and you can't get rid of that dent. You know what it's like to fix metal that's dented. Or you might have just difficulty replacing it so that it looks new again. So if we don't have to remove the outside, we don't really want to, but we still need to see the inside of the walls to be able to inspect them for compliance. So I'm recommending we remove the interior cladding and then replace that with nice new flushed gyprock. So when we take the internal cladding away, we want to be able to see the wall framing inside. Now, the wall framing will need to be compliant with an Australian standard timber framing code for cyclonic conditions, AS 1684.3. You want to write that down, it'll be in your report. I have it printed out here rather than going to the standard itself because we use it quite regularly. It's not a very exciting looking standard. It's simply just tables and tables and tables and tables and tables. It's quite significant, so don't feel like you have to read it from front to back. 1684.3, residential timber-framed construction, cyclonic areas. 1684.3, residential timber-framed construction, cyclonic areas. Pardon? No, it's the Australian standard. So this is over and above the NCC. Pass it around so you can have a bit of a look. Yeah. Now I haven't printed the entire standard. There's a whole bunch of supplements that goes with it. But I have printed some.
Are we proposing also the square hollow section?
Columns? Yep.
Yeah, so we have to just add it on there.
Yeah, we'll come back to those though. Don't panic too much. We just put that as a bit of an aside. I just needed to reference those so we had something to connect the bracing to. And I've sort of skipped back up to the wall framing.
You can weld to those, but you can't drill through them.
To the hollow section. You can drill through them, but you have to be careful because anything you make a hole in, water can get in. Yeah.
Imagine old mate trying to put up some shelves 10 years down the line and extra into it.
Yeah, it's likely. I went to an architectural firm yesterday to assess a student from last year's work placement, and they use Bluebeam as well. I was like, yeah, everybody's learning the right stuff. All right, very quickly, I'm going to skip in the NCC. I'm just going to take you straight to 3.4 framing. I want to show you some images that I'm hoping they still have in there. There we go. All right. So, in both the NCC and also the Building Construction Glossary of Terms. Remember the other Australian standard, HB50 it's called, is a glossary of terms. There's a huge range of illustrations at the back as appendices in the glossary of terms. So if you look here in the back after Z, there's roof truss designs, roof tile shapes, stairway shapes, doors and windows, different courses, so when you have rows of bricks you can have fancy grout that looks really pretty, different bolts and screw connections, all sorts of different materials and pictures, and they also have pictures of the framing like I've got up on the screen, the roof framing and the wall framing. They've got details of construction, wall framing, where are you? All the different detailing, how to connect brick veneer together, what rises and goings look like, different shapes of bricks and block layouts. There's my roof again. Here it is. So the one on the screen is also in the Building Construction Illustrator. This is a separate sheet of paper. If you want to make a copy, you're welcome to. It's got all the labels on the side. This is traditional framing. So remember, this is not cyclonic framing, what you can see up on the screen and what you see in here. This is NCC framing that works for everywhere except us, and then you have to apply the extra that the Australian Standard 1684 asks for. is our bearer. Now this one's all timber. We have a PFC bearer in our construction, but this horizontal member is the bearer. It bears the weight. That's how to remember. Directly above that, here these smaller pieces, typically the bearer is larger. These smaller pieces here, you'll see has a label there, 14, should say joist. Let's just scroll down. Floor joist, yes, these ones. In Darwin, the maximum distance between them, centre line to centre line, is 450 centres. So floor joist at a maximum of 450 millimetres between the centre line of each one. The bearers are determined by the span the floor joist can achieve, but the centres between the floor joists are a maximum of 450 centres. Write that down, you want that in your report. You need to check and verify that the floor joists are in fact a maximum of 450 centres. Maybe the code changed between when the building was built and now. And you'll notice there are two, a double floor joist directly under the wall. Can you see that there? And it was the same for our chain of strength diagram, wasn't it? A double floor joist under the wall. Because obviously when you have this same sort of timber laying down as the bottom plate of your wall frame, because your frame isn't just a whole stack of verticals, it has to have a top and a bottom. If you've got your bottom plate here, it has to have something to rest on, and you need two so that it's got somewhere to sit. But typically you'll space them apart so that you can have somewhere for the floor to also sit. See how it's notched out there a little bit? So the flooring can sit there. You might use structural ply or CFC, a big thin sheet of flooring there, and it'll have somewhere to rest and be fixed. But that's also handy, that little gap, because the hold down rod can just slot right through there and down to the bearer. So it's quite convenient.
Would they be of two different sizes?
No, they're usually the same size. Structural stud framing and the floor joist can be the same size. Yeah. Sometimes they're a little taller. And then we've got these vertical here. These are the studs. Now this one's a jam because it's adjacent to an opening, but it does the same work. Where's my little label for that? So 11 here, jam stud. So it's a special type of stud. This vertical piece here and this vertical piece here. But 10, which isn't adjacent to an opening, is just a regular stud. And see how close they are together? But see here, David, where you were talking about doors and windows, what happens? So then you have a gap underneath the window and above the window, and you simply divide that up at 450 centres and put verticals in to replace what would be missing because of the opening. And then you've got number 12, which is the sill, a sill trimmer, they've called it, but the sill. And the number 7, which is the header, they've called it a ledger, so we call that a header.
What I was kind of getting at is like sometimes, especially when I was in Australia, the houses over there in Bombay were one whole wall is glass.
Uh-huh. So what do you do then? Yeah.
There's no real tie down.
No. No, there isn't. Correct. Yeah.
That's okay.
It's achievable by increasing the hold down in other places. So the engineer would have to come up with a solution where the total hold down was sufficient for the uplift of that building for that size in that location. Yeah, so it's quite special. It's a very good question. So big wide openings restrict the amount of hold down you can have. Absolutely true. And then obviously the load has to be spread right across that opening as well and down the sides, which is another issue. So the engineers are starting to look like the good guys, aren't they?
What's the maximum span for beam?
What's the maximum span for a beam? Depends how big the beam is and what the load is doing. Case by case. Yeah. We've got some span tables we'll look at in 4005 to show some that you can size up yourself on a smaller scale, but once it gets beyond residential, it's up to the engineers. And here the engineers have to check it anyway, but you can at least suggest. So perhaps if we were rearranging the location of the columns, we would look at that now. We'll keep that for later. The other thing that you'll want to see is number 9, a nogging. See this horizontal member in the middle? So just like the tall, thin columns that are subject to raking, tall, thin studs are also subject to raking as well. Now this nogging is just mid-span. So there's the bottom plate, the top plate, and the studs holding them apart so the ceiling doesn't sit on the floor. And then we've got this row of noggings in the middle. And it doesn't cut the studs, it sits between the studs. That's very important. For structural walls, for timber or steel, we'll have 2 rows instead of 1. So at 900 centres, a third and a third, because it's 2.7 metres high. So a row of noggings here and a row of noggings here, rather than the centre one. Now what that means is if the cladding is still on the wall, you can't tell if it's a load-bearing or non-load-bearing wall. If it's the exterior of the building, you can be confident that it's load-bearing. But internally in frame structures, they're all the same width. You can't tell from the outside if something is load-bearing or non-load-bearing. So if in doubt, assume it is. Whereas blockwork gives it a bit of a way because the very narrow blockwork walls are typically not load-bearing. If it is load-bearing, you'll see 2 rows of noggings rather than just the 1. But you also need an extra phenomenon called K-bracing. So we've got bracing between our columns downstairs, but we also need to have bracing in our walls upstairs. So we've got a corner stud, and this is just a single wall, and we've got a series of studs at 450 centres, and we've got a bottom plate for them to sit on and a top plate for them to go across the top. Now, I shouldn't draw just single lines to represent materials, but if I run my hand up and down, I'll make a big mess of it. So I'm just using a single line to represent a thickness of material. So we've got our studs. Now, we talked about having 2 rows of noggings for an exterior wall or a structural wall. That's terrific, but it's all squares. So if I was to stand here and push on that side, I could probably get that wall to fall over in this direction. So it would go this way. And everything would just domino effect over. So I was particularly cranky. But if I was to put diagonal bracing in that wall, perhaps in that design, there's lots of different shapes and sizes you can do, but to create that triangulation, it's much less likely to rake. There's lots of different ways that you can do K-bracing. If you've got more than 3 panels, this long diagonal is the most efficient. So you simply put either timber or steel in between, or you can use what's called a strap or speed brace. It's just a long roll of flat steel that's about 30 mil wide. Looks just like this, but on a roll. This is bent in a funny shape, so just ignore that. But it sort of looks a bit like this. It's galvanized, and it's pre-punched with lots of holes already poked in it, and you put it from the top to bottom, and everywhere it crosses a piece of material, you fix it. It's different for steel frame because you have a weldable ability, or you can tech screw in. This is for timber typically. So for K-bracing, you would just use more steel in between. Yeah.
With noggins,
Yep.
in that situation, the bracing, the structural wall,
Yep.
are you allowed to offset each second brace to make it more easier to...
Yes, it has to be. Yep, a little bit up, a little bit down.
Yeah.
A little bit up, a little bit down. The practicalities of the construction, obviously, you need to be able to get in there. So, yeah, they just offset the length, the width of itself. Yeah, I haven't gone to that trouble.
A really good nail gun and the damage.
All the way through, yeah.
Because your noggins are the same,
Yep.
nailing through, It's only going to cost you actually weakening the timber.
Yeah.
Yep, quite right. Little bit up, little bit down. Just to be really fancy. So 900 centres, because overall that's 2,700 high.
Max, yeah.
Maximum 900 centres, yep. So in addition to your 450 centres, studs and hold down rods, noggings in structural walls at maximum 900 centres, and K bracing as per engineer's specifications. They call it a K because you can actually do it, I'll draw another diagram, you can actually do it like this. And you can do it like this. You actually go to the centres, apologies. And they kind of look like Ks. If you've only got one stud, you go zigzag, zigzag inside that stud, and it looks like a K, so that's why they call it K bracing. So K bracing as per engineer's specifications. So sometimes you'll get an engineer that will say, you propose where you'd like to put the K bracing and then I'll approve it, and others will draw it for you. Some of them will tell you which walls you have to have it in. Sometimes you don't need it at all in every wall, but for this one I suspect we probably will need it in every wall. Now it may not be there, the K bracing. That might be something that hasn't been in place when the house was originally built. We'll have to see when we open it up. I expect the hold down will be there, but I'm expecting some of the rods will have deteriorated and they'll need to be replaced. But I'm not expecting to see the K bracing. An alternative, there is an alternative to K bracing, and this is what we might see, but I'd be impressed, is rather than using interior K bracing, you simply put structural ply over whole sections. So that ply then creates a similar bracing effect, but you have to connect it a lot. The screws have to be really close together to have the desired effect, and it has to be structural ply. It can't just be any old timber. It has to work structurally. Plywood is very thin veneers of ply glued together in layers. I think you've already seen that in cross-section. And structural ply is created where the grain of one panel goes in the opposite direction to the panel beneath, and it just goes back and forth within the one piece, and it creates a very stable cross-section that you can then use on the inside before you put the gyprock on to create bracing. So it can either go on the outside before the steel framing, or it can go on the inside, or both. So there's a chance we might find that, but probably not.
So they're going to have to like rip out the existing walls to see what bracing is.
You're going to have to expose the internal bracing regardless, absolutely. The trick is which one, inside or outside. It's obviously easier to work from the inside. You've got a floor to stand on, it's shaded. You want a nice aesthetic look on the inside when you're finished, so creating a new finish inside is most likely going to be what the client wants, particularly if the outside is still in reasonably good condition. And from what I've seen, the majority of them are in still reasonably good condition. There are a few with a few panels missing. You obviously wouldn't buy that one. You would pick one that the cladding on the outside was reasonably intact.
Yeah, there's no way to inspect a frame system unless you open it up. There's just no way to do it.
Unavoidable, yeah.
We don't have the... I did recently ask the surveyor have they got to that point yet, that they have got some sort of piece of equipment that can go in and scan and give you a model of the frame.
Infrared or something, yeah. No.
It doesn't exist. I'm waiting for that day to happen.
Yeah.
Yeah.
You'd have to drill so many holes to put in there, you might as well just take the cladding off. Yep. Does anybody have any questions about, sorry? They're stud finders. They're not as fail-safe as I'd like, though. Yep. I've seen a couple of spots where my dad thought he'd found the stud and missed. Nope. Oh, no. Yeah. Finally got it. That's what he did. Three little spots.
But you also want to know, like, the dimensions of the timbers. You want to know where all the K bracing is. Sometimes the stud finders can beep, and then you hit a bit of bracing. And
you don't really know what you've got.
Where that bracing is.
Yeah.
You've got to see it. You have to open it up to see it.
So the other thing that the Australian standard will tell you is how big the timber needs to be and what strength it needs to be. So it's very easy to manufacture, I won't say easy, but it's easier to manufacture steel to a very predictable, known strength capacity. That PSC, it has a known strength capacity. But timber is a natural product. We can't say to a tree, can you please grow to a certain strength capacity? It doesn't work like that. So timber has to be graded, and this is something that you'll come across when you do your timber research. Timber has to be graded, and then you have to use that certain grading in your structure according to what the engineer wants to achieve the strength that you need. So the timber has to be the grading and the size to achieve the structural stability that it needs to do the work that it's expected to do. So a tile roof is very heavy. There might be an additional requirement to have stronger timber under tile roof conditions. We have a sheet roof, it's much lighter, so our requirements for the strength capacity for the imposed load or the dead load that's coming down on the walls might be a little less because it's steel sheet, which is lightweight.
I'm assuming that this house would be built after the cyclone. So it would be built to cyclone.
Not necessarily. Not necessarily. Things before cyclones were before Cyclone Tracy. When you say before the cyclone, you mean the cyclone. That is our benchmark. Everything's either before Tracy or after. Things before Cyclone Tracy were built according to cyclonic conditions. We knew that there were cyclones before that. They weren't built to Cyclone Tracy conditions, perhaps. But they were built to the code at the time. But the code is different now. Yeah. So we still have to check it. And the deterioration of the materials from then might have occurred as well. So we're looking for two things.
That's why it probably won't have the K-brace.
I don't imagine it will, no. It'll have the noggings, the 2 rows of noggings. I predict they were around then, but I don't think the K-bracing. But the ply may have been in place. I've demolished a house in Larrakia with my dad, and it had the structural ply, and that was around the same era. Oh, did you? Really?
It's phenomenal. It is like, to think that they just moved all that food in there, and some of them are still good there.
Yep. Yeah, you'd have to be choosy, but you just pick a good one. There's plenty to choose from.
There's a couple there already with verandas and everything.
Well, yeah. There's a couple that have got some really nice shape, little gable fronts and things.
They've removed it into sections as well, so there's like a section full of staircases.
Oh, is there?
Yeah.
All the stairs they took apart. Yeah, okay. Yeah, you probably don't want the stairs. They're going to be non-compliant anyway, I suppose, aren't they? Yeah. Cool.
Kind of eerie.
Yeah, it would be a little bit eerie. That's fair.
I noticed that they got beside that paddock, then there is the demountable paddock, and then there's another new section now I noticed last weekend. Did you see a little bit further? Heading out of town a bit further. There's another lot there where they're reconstructing some more, and so there are different shaping and everything again.
The guy who bought that, he must be so loaded.
Scott? No. Yeah, it is. One of the past students works for him. I don't know if I would go with so loaded, but...
How did he get the whole lot then in the first place?
I think he bought them off the guys that bought them in the first place, so there might have been a deal done. Who knows? Yeah. Have some lunch. Come back in an hour.
They started about 60 grand now, I think. They were expensive at one place. 50